Good morning, everyone. In today's lecture, we will continue what we have started. We will look at the magnetic field, the induced magnetic field, and the principle of the superposition for the magnetic field. And then we will go through a device that will introduce a device that's called solenoid. We'll explain what does the solenoid mean. And then in the coming lectures, we will look at Ampere's law, the motional electromotive force, magnetic flux, and Faraday-Lenz's law. So let's start with the principle of superposition for the magnetic field. We have seen and derived earlier the expression for the magnetic field for the finite wire, and then we extended it to the infinite wire. And we have seen that the magnetic field for an infinite wire is giving as B equals to mu naught I divided by 2 pi r. And that in general, we give it theta. So in general, we say the magnetic field is a mu naught I divided by 2 pi r, where r is the distance from the point of interest to the wire. And then we say usually theta hat, which means that it is going in the unit vector direction of the theta around the wire. Now, this theta here in my case, where I have a Cartesian coordinates, this is x, y, and z pointing out of the page. In this case, if the wire that has the current going through is in the same plane of the point of interest, P here, which both of them are in the XY plane. In this case, using the right hand rule and assuming that the current, for example, is going in this direction. In this case, if we assume the current going in this direction, we can see that the magnetic field is pointing here at point P using the right hand rule, where in this case you use your thumb for the current, the straight component, because the magnetic field will be circulating around this wire. Then the fingers are going to define the direction of the magnetic field. So in this case, at the point P here, all the magnetic field would be pointing out of the page at the lower side because of the rotation of the magnetic field. At the lower side, the magnetic field would be pointing into the page. So if I'm looking here at the point P and one side of the wire and assuming that the current is going in this direction, then the magnetic field would be given by this expression where the unit vector is k hat. Now, if I'm looking at a semi-infinite wire, which is basically half the wire, trying to cut the wire right here at the point P, if I cut the wire right here at the point P and only took one side of the wires, in this case, the magnetic field would be half of the magnetic field for the infinite wire. The direction is not going to change. The direction is always perpendicular on the wire and the point of interest in this case. So the magnetic field is always perpendicular on the XY plane since the wire and the point are in that plane. That's why now the magnetic field for the semi-infinite wire would be half the infinite wire. So here would be mu naught I divided by 4 pi r, and the direction is going to be the same. Now, if we look at half a loop, remember we derived the expression for the loop, and if we assume that the loop does exist in the xy plane, then the magnetic field at the point here at the center of this loop would be given by the B loop vector equals to mu naught I divided by 2r. And again, since usually when we write the loop, we say that the magnetic field for the loop is mu naught I divided by 2r, where r here is the radius, and then we say n hat because we did not define the direction. So this is the general expression for the loop. The n hat here means it is perpendicular on the loop. So for my case, if I am to have a circular wire in the xy at this point at the center, then the expression would be here. N hat would be k hat if the wire is going, assuming the wire is going in this direction. Now, if I have a half a loop, and assuming the wire is given here in this direction, so this is I, this is I. In this case, my expression for half a loop would be exactly half what I found for one complete loop. And in this case, the magnetic field would be mu naught divided by 4r. And here the unit vector is k hat, which means that the direction of the magnetic field at the center of this half loop is pointing into the k hat. Now let's look at this example. In this example, we have the current going this way, and as you can see here, the wire is making a curve and then coming back. So now I can approximate or look at this problem from the superposition point of view as the following. I can treat this one as a semi-infinite wire and another semi-infinite wire and a half loop here. And here, now, if I am to call this one at all of them, I want to calculate the magnetic field right at the point P. So if this semi-infinite wire here is, I'm calling L1, then it is contributing to B1, and then this one is L3 contributing to B3, and then the half a circle is L2 contributing to B2. In this case, if I am to write the magnetic fields due to those wires, so let's start with the first one, the semi-infinite L1. In this case, this is going to be mu naught I, the current I, divided by 4 pi again r, which is the distance from here to here. The distance from here to here is r as well. And now the unit vector. So if the current is going from the left to the right, using the right hand rule where the current is taking the thumb direction, then the magnetic field would be taking the fingers. So in this case, the magnetic field would be pointing out from this side at the upper side and pointing in and this side, which means if I take the coordinate as x, y, and z this way, then in this case the magnetic field at the point P would be pointing in the negative direction for K. Also, the magnetic field due to the semicircular wire would be half, so mu naught I divided by 4r, and the direction is, again, the current is going this way. Now, using the right hand rule where the current is taking the direction of the fingers, then the thumb would be pointing into the page. So this one is also minus k hat. And now B3 would be also mu naught I divided by 4 pi r. And also, if you try the right hand rule, you will see that the magnetic field is pointing into the page. Then the net B net would be the summation. So B1 and B3 are equal. So this is going to be mu naught I divided by 2 pi r minus k hat plus mu naught I over 4R minus K hat. So this is the net magnetic field due to those three wires that we classified them as two semi-infinite wires and one half circular wire, and the superposition was applied to calculate the net magnetic field at the point P here in this case. Now, let's move to the solenoid and introduce this component in our course. The solenoid is a stack of loops that are made from the same wire. The wire is insulated, so there is no short circuit here between those wires touching each other. There's an insulator in between. They are tightly wound such that they look like a spiral of wire. So when the current enters in one terminal here, it leaves from the other terminal right right here. Now, if we look at only one loop, the one that we have seen before, we can see that the magnetic field right on the axis that goes in the center of this loop is, as you can see here, straight, while the point at the center of this loop would be the maximum. However, if we look at the sides of this loop, we can notice that there are here some closed lines that defines the magnetic field as well, right here, and we have seen that before. So in this case, if I look at this point, the magnetic field will always be tangential on that path, which means that the magnetic field here will be parallel to this axis right at here where the slope is 0. Same thing is happening here. The magnetic field is straight this way right at this point. And as you can see, once you come closer to the circle, then the path is going to expand further. But again, at any point, the magnetic field is tangential to that point. This way. So this is only for one single loop. Now, what happens if I put one loop on the left and one loop on the right, make them three loops? So I am extending now my loops. So in this case, what's going to happen? Notice that the current direction will be the same. In this case, they're entering from the bottom, leaving from the top, and so on. So it goes from one out, then get out of one, comes into two, gets out of two, and goes into three, and so on. So if I am to look at two distinguished points here, one of them is right here at this point. So this one, the magnetic field is due to this field line is the B2. However, if you recall, B1 is coming from the line. So this is B1, and also B3 is coming from the loop number 3, and it's doing like this. So now I'm looking at this point right here. It will be the superposition of those three magnetic field, B2 from loop number 2, and B1 from loop number 1, and I have B3 from loop number 3. Notice the direction of the magnetic field. So right at this point, the B2 will be opposite. So here I have the projection of B1 and the projection of B2. It's going to result into a magnetic field that is opposite and canceling B2. That's why we will say that at this point the magnetic field will be weak. However, if you notice the contribution to the magnetic field from all three loops, you will see that B2 is maximum, and then comes B1 and B2 being the same due to the symmetry here. So I have strong field right at the center, and I have weak field right outside the loop. Now, if I increase the number of the loops further for this solenoid, I will end up with the following. You can see now this is the magnetic field coming from this field line here. However, this one is coming from this one, and this blue one is coming from the one before, and so on and so forth. So now if you look at the magnetic field outside the solenoid, there will be weak at every single point here. The magnetic field right at those points will be relatively weak because I have the magnetic field coming from the solenoid from this loop as being cancelled by the magnetic field coming from the loop before and the loop after, and this is going to result into weak magnetic field outside the solenoid and strong and almost uniform magnetic field right at the center of this loop. The more the more loops you add, the more uniform the magnetic field becomes. So let's look at this question. Here we have a solenoid that has a magnetic field inside due to the passing of the current in this loop. Now the question is asking in what direction is the current flowing through this solenoid at the position of the red dot, which is this point. Now we can apply the right hand rule here. And in this case, we will be use the thumb for the component that is straight, and we will use the fingers for the component that is circulating. So if you look at the solenoid, we can see that the current is the one that's being going in circles around in this solenoid. So I will use my thumb for the magnetic field that I can see here. So it will be going, this is the direction of the current, and then the fingers are going to define the direction of the current. So the thumb is the direction of the magnetic field, and the fingers are the directions of the current. So I can see that current is entering at this side, leaving at that side, and that's why the correct answer is the current is coming out of the page at the red dot. Now, as I said, this solenoid becomes more ideal when those numbers and the length of the solenoid increases to relatively high number. In this case, ideally will be an infinite number with an infinite length. In this case, the solenoid will be assumed to have a uniform magnetic field inside it. So we will be treating long solenoid, we'll be treating it as an ideal solenoid that has a uniform magnetic field inside. However, the magnetic field outside in the ideal solenoid will be zero.